Day, which is the 12th. And it's going to be on the ocean floor features and sonar and sounding. So everything we've studied about the ocean floor, as well as what we're doing today, and we'll go in depth a little bit more this week so that you have enough information. Your agenda for today will be sonar and sounding, and your homework is to study. So you have a sheet in front of you that looks like this. Now you need to have a highlighter, a blue and a brown crayon. But first, let's talk about what this sheet is. We're going to be looking at sounding, which is the measuring the ocean floor. And you're going to be using something called sonar. Now, sonar actually stands for sound, navigation, and ranging. Make sure you write that down under your title. The word sonar comes from the S-O in sound, the N in navigation, the A in and the R in ranging. And that's how we get sonar. Now, before we discuss how do we measure the depth of the ocean floor, let's take a look at a little short video of how to measure the depth of the ocean floor. So let me pull that video up now. Give me a second.
For the most part, we don't know what lies beneath the surface of our oceans. Most of the waters and ocean floor remain unexplored. But with new technology, projects are underway to find out what lies in the deep. Since 2004, a team of scientists has been cruising the Caribbean surrounding Puerto Rico, as well as St. Thomas and St. John Islands in the U.S. Virgin Islands, to create a comprehensive map of the seabed. NOAA, the National Oceanic and Atmospheric Administration, is the U.S. agency in charge of mapping, protecting, and managing some of these waters. They're updating old nautical charts.
So a nautical chart has soundings on it, just, discrete locations. But our map is continuous. We can see the ups and downs, the ridges, the ledges of the sea bottom. And all of that is important information for a manager, as well as to make the linkages between the seafloor habitat and the types of organisms that are using that.
The waters off the coasts of St. Thomas and St. John have important habitat, including coral reefs. The waters have protected areas as well as areas where commercial fishing is allowed. Each year, the NOAA ship Nancy Foster zigzags through the water, using sonar to scan the seabed. The ship emits more than 3,500 pings per second in a wide fan, creating an image as if painting strips of data across the seafloor.
Now, if you take a look here at this boat, what the boat is doing, it's sending a signal down and it's receiving a signal all the way across sea level through the ocean floor so that it can get an accurate depiction of what the ocean floor looks like.
Weeks of back and forth sailing in a pattern much like mowing a lawn yields traditional chart information, including bathymetry, or depth, in incredible detail.
All right, so that is what we're talking about here, measuring the ocean floor. Before we do that, let's just take a look at this picture. In this picture, we need to label sea level, transmitter signal, receiver signal, and ocean floor. So when we look at this picture here, we can identify this area as being sea level because it's the top of the water and it's what the boat is traveling across. Down here, this is your ocean floor. Now we noticed in the video it said that the boat goes back and forth for weeks, but it sends several signals as it does. Now, what happens is it sends a signal down. This would be your transmitter signal. When that sound hits the floor, it bounces back up to the boat, and this is your receiver signal. This is like echolocation of a bat or a dolphin. They send signals out so they can know how far of a distance they are between themselves and another object. So every time it sends a signal, it waits for it to come back, and it records the amount of time it took for it to all come back to the boat. Now, there are certain things that could get in the way, for instance, fish, treasure that has sunk, like other boats that have sunk or different things like that. There are things that can get in the way. That's why they have to go coast to coast or back and forth and send several signals and then compare the data that they receive. Now, the ocean floor is not going to be perfect, but it'll be as accurate as possible as we can get it from measuring the depth with this thing we call sonar. And this is how oceanographers do this. So let's take a look at the bottom. It says much of the ocean's topography has been mapped by the use of devices such as sounding. I want you to highlight that, because sounding is how we measure the depth of the ocean floor. Sometimes they do it from an airplane as well, and they send the signal from an airplane and wait and see how long it takes to get back. And they use the thing called sounding in sonar. So in this method, sound is sent from the ship's transmitter to the ocean floor at an angle, like it shows in the picture. When the signal hits something like the floor, the signal bounces back to the ship at the same angle and is picked up by the ship's receiver, like it shows in the picture. The speed of sound in water is 1,524 meters per second. Highlight that, because that's going to be our constant. That's our speed of sound in water, also known as our velocity. Using this information and applying the formula 1/2 t times v, go ahead and put your t in parentheses. And that's what that means, 1/2 t times v. The ocean depth can be measured and mapped out. So we use this formula here to figure out the depth of the ocean. Now notice it's 1/2 t. It's 1/2 the time. Because we do not want to know how long it takes for the entire receiver to come back and the signal to come back, we only want to know how long it takes from it to go from the floor back to the boat, because we're measuring the depth of the ocean floor. So using that formula, we can measure the depth, and we can also map out and make a topographical map. Now, a topographical map has the word topo or top, and it has the word graph. Top, when you think of top, you think of surface, at the very top surface, and then you have the word graphe, which means to draw or a picture, like the word graffiti. So when we look at topographical map, then we're actually looking at a surface picture. This would be considered a topographical map because it's a picture of something that we're trying to represent. So a topographical map would actually be a two-dimensional picture or representation of a three-dimensional land surface or land structure. So we are doing this, measuring the depth of the ocean floor, making a topographical map so that we can draw a two-dimensional picture of the ocean floor, and the ocean floor is our three-dimensional land structure. All right? So now let's look at the other half of the paper. The formula for measuring ocean depth, when you look back over here, Here's your formula. It's half of T times V. That equals D. So D equals half of T times V. D measures depth, and it's measured in meters. T is time, and that's measured in seconds. Velocity, or the speed of sound in water, remember that's our constant, and that's 1,524 meters per second. M/S stands for meters per second. So it takes 1 second to go 1,524 meters. So in water, speed travels 1,524 meters per every second. So now we need to look here. Here we have data that represents sonar signals received by a ship traveling in a certain area of the ocean. We're going to use this information to create a topographical map of the ocean floor in that area. So what happens at location A, the boat sent a signal, transmitter signal, and it received the signal, and it took 1 second. At location B, it did the same thing, and it took 2 seconds, all the way down through location J. So we need to find the depth at each location. So down at the bottom of your paper, I've given you space to figure out the depth. Just do one problem. So let's do the first one for location A. Again, the formula is D equals 1/2 the time times velocity. So let's plug in our numbers. 1/2 the time at location A. Okay, so using this same formula, again, we're still doing location A. So we have 1/2 the time at location A is 1 second. So we have 1/2 1 second times V, which is actually 1,524 meters per second. The depth equals half of 1 second, which is 0.5 seconds, times 1,524 meters per second. And that's going to give us a depth of 762 meters. We need to put this number for depth at location A. Doing this same formula will come up with the rest of the location depths. So the depth at location B is going to be 1,524 meters. That's for 2 seconds. Notice that G, H, and I all are 2 seconds, so they're all going to be 1,524 meters, 1,524 meters, and the same for I. Notice that location A is 1 second, and so is location J. So that's all going to be 762 meters. When we use the formula to figure out location C for 3 seconds, we then get 2,286 meters. For location D for 8 seconds, we're going to get 6,096 meters. For location E for 6 seconds, we're going to get 4,572 meters. And location F for 4 seconds, we're going to get 3,048 meters. So again, when the boat travels and sends a signal down, waits for the signal to come back, they take that time, they divide it in half, and multiply it by the speed that sound travels, in water. So we have all of our data there. Now, looking at our data, we want to go ahead and kind of put them in numeric order. So although we have these different plots, we do want to kind of put them in numeric order. So our shortest depth, or our shallowest depth, is 762 meters. Our next depth after that comes 1,524 meters. All of those and those. Then we have a 2,228 meters. Then we have a 3,048 meters. Then there's a 4,572 meters. And our steepest depth, or deepest depth, is 6,096 meters. So we're going to use that in just a moment. But when you flip your paper over, you have this side. And it's asking us to plot the depths on the graph below from our data we calculated on the other side for each location to create a topographical map. Now, our topographical map that we're doing, we're going to draw a picture. Remember, we sent a signal down to the ocean floor and waited for it to come back. So our picture is going to be a picture of the ocean floor. Now, in doing this, give me a second, let me adjust this so you can see the whole thing. We need to label our sea level. So this top line, this is the very top where there's no travel. This is our sea level. We also want to label our axes. We have our two axes, one here and one there. But we need to label them location and depth. Considering that this is sea level and this goes down, then this over here would be our depth. And it's measured in meters. Moving this way, our boat travels along sea level this way. So these are our locations. The depth here, where there's no travel, it's no depth here, this would be 0. Then looking at our locations, let's say our location A, our boat traveled and stopped at location A there. So we'll put location A, skip a line, location B, skip one, location C. So we're just going to list our locations, but only skip one line after each. So we got D, E, F, G, H, I, and it goes all the way to location J. So we have all of our locations mapped out. Now remember, our depths were these numbers. Our shallowest depth should go closest to the top, and our deepest depth closest to the bottom, because that's the deepest. So it doesn't have to have any specific order that it goes, well, not order, it doesn't have any specific rhythm that it goes, so it doesn't have to skip one line or skip two lines. We're just going to kind of plot it and take a guesstimate where we think each number should go. So I'm just going to skip 2 lines and I'm going to put 762 there. I'll skip about 4 lines and put 1,524 there. Our next number is 2,228. So I'll skip just maybe 2 lines or 1 line and I'll put that one there. My next number is 3,048, so maybe I'll skip 2 lines and put that one here. Notice I don't have to label it meters because I've already done so over here. My next one is 4,572, so maybe I'll skip another 2, maybe 3 lines, 1, 2, 3, and put this here. And then I have one that's 6,096 meters, So I'm going to skip 1, 2, 3, 4, 5 and put that here. Now we're going to look at the front of our paper where we have our depths at each location. And we have to plot that. So location A is 762 meters. So from location A, I'm going to go down to 762 meters and put a little dot there to plot that. Location B is 1,524 meters. So from location B, I'm going to go 1,524 meters deep. Location C is 2,286 meters. So I'm going to go to 2,286 meters deep. Location D is 6,096 meters. So from location D, I'm going to go all the way down to 6,096 meters deep. Location F is 3,048 meters. I'm sorry, I skipped E. Location E is 4,572 meters. Now location F is 3,048 meters. Just like math, we're just plotting numbers. G, H, and I are all 1,524 meters. So they're all going to be right along here. And J is 762 meters. So J is here. Now we just have plots. So we have to connect these because we are mapping the depth of the ocean floor. So we have to connect the dots from A through J going in order. So A to B, B to C, and continue on. You don't need a ruler. Now when you look at it, it just looks like a line graph. But remember, this is a topographical map, so we are mapping out a two-dimensional picture representing a three-dimensional land structure. So the ocean floor, remember, you got a boat up here traveling from location to location, sending a signal down. When that signal goes down, it comes right back as soon as it hits that floor. So this is the ocean floor. So everything under here is land. So we need to color our land brown. And this is your ocean floor. Which means that everything above there, this is water. So when we now put it all together, if we look here, if that ping was sent down from here, a signal, and we had this, and we look at our structures now, this would be the coast. This would be the beach. So then this would be representing our continental shelf. This would be our continental slope. And we can also say it probably goes all the way down to here, or we can say right here, end of our continent, this would be the continental rise. Then we have this deep depression. So this would be an ocean trench. And you don't have to always have all of the features, and they definitely don't have to be in order. You will always have the continental shelf, slope, and rise, because that is entering into the ocean. That's our entrance way into the ocean. Now let's say, don't draw this, but let's say we had more data to plot. And let's say our data did this. Then here would be a seamount. Or let's say our data did this. Then now we would have another continental shelf, another slope, and another rise, and then this could possibly be an abyssal plain. So that means that this would be another beach, which means that we would have traveled coast to coast. And this concludes the lesson.